Welcome to our NPTEL lectures on the power quality improvement technique. Today we are going to discuss the first part is the voltage source converter and current source converter. We have discussed in detail about the voltage source converter and its predominance in the different kind of drives applications, but we shall also visit that CSI current source inverter, and also it can be applied to the different kind of current mitigation technique, and it is a perfectly suitable for the STATCOM and the shunt active power filter. So, but problem lies that we do not have current source, we have a voltage source. So, for voltage source inverter, as the full form denotes, the output voltage is constant with the output current, change with the load type or any other values of the component, and in CSI it is just reversed, and the current is nearly constant and the voltage will change according to the load. So, that voltage will be the whatever the load you connect it to. So, otherwise it will give a constant current. So, this is the how it will be realization. Please understand, when you have made by VSI, depending on the load, you generally have a bidirectional switch, and generally switch conducts for the positive up cycle, and you require to have a bidirectional current flow and unidirectional voltage flow. But here we require a unidirectional current flow, and this diode will ensure that unidirectional current flow has been achieved. So, this is the current and ultimately will flow like this, and you turn it on, this thyristors, automatically it is a auxiliary commutation which you have studied into your power electronic circuit. So, ultimately once you turn on, this current will go through this because of this capacitor, and so current will transfer to the TH2 unless this given a trigger. So, this current will flow. So, this will be the value of the current. So, you will get a bidirectional CSI inverter, and how you realize it? Very simple. You will have a DC source, with the DC source you will have a very large inductor. This is the challenge, getting a very large inductor, and unless you get a very large inductor you cannot make a constant current source. But you see that it is inherently short circuit protected. You always have a short circuit protection and all those issues. You have a problem of the leg short in a VSI. So, you can have a you can have a more reliability on it, at least it does not have a short circuit condition. So, and current is unidirectional, current can flow in the one directions, and it should give an alternative path to flow for the bidirectional in nature. So, this construction of CSI is quite simple, and also operation of this CSI is also simple, but only challenging task is that you require a very high value of the inductor to make a constant current source. But you can ask that, so this is a perfectly suitable for this STATCOM or the shunt active rectifier, where you require to inject a current into the parallel to the load, so that it can deliver this kind of configuration. So, as let us come to the basics first. Applications we will talk about in STATCOM or or in active power filter. So, VG1 and IG1 and IG3 have been gated. So, current will flow through it with a constant value, and thereafter Ig2 and Ig3 are been gated. So, then this kind of pulse will be there, and please go back. This is the voltage across this capacitor, and it will be having a negative voltage initially. Initially, it will be charging and it will close to hold the plus VCO. It will hold till the other thyristors has been triggered. It will continue to do that, and ultimately the load current will have little charging and a discharging profile that will come into the picture. And this is the IA1 and the diode. This is the current of IC1, that is the capacitor current, and it will be 0. Again, when it is the T2 and T4 are been triggered, again it will bounce back and go like this, and this is the ID1. Current has to be unidirectional here, because diode cannot allow current to be bidirectional. So, current will flow like this. Thereafter, the diode D2 will conduct. For the small durations, both the diode conducts D1 and D2. Let us see this figure. So, these both will conduct while charging the capacitor. So, this is the 3 phase realizations of this circuit of the CSI. So, you require to provide the auxiliary commutations to make it 3 phase. So, you can do that. So, this is C1, C2 and C3, these are the capacitors that will ensure that auxiliary commutation has been achieved. And essentially what you will do, you will have a inductor followed by VDC, and that can be considered as a constant current source. So, this is the overall figure. So, this VDC is essentially this, and since there is no losses across it, so we can assume this voltage, we legitimately take this voltage to be VDC, and thus you can fit the current IIBIC with the RL load or any kind of load, and this is a CSI operation. So, you want that a 30-degree operation. So, sin 30, where if you have sin 30 means, if you please recall your 3 phase waveform, and at sin 30 A and C makes the crossover and B is the most negative phase. So, to mimic it, so T1 and T3 will be triggered and T6 will be triggered, and there you will have this there you will have this current to be flow like this. So, students are requested to simulate this circuit and with the thyristors, and they are familiar with the 120 degree mode of conduction and 180 degree mode of conductions. For the VSI, I want them to same task to be performed with the CSI, and since voltage is going to be a square wave, but what I essentially wanted to have a current profile and then its harmonic spectrum. This I left for the student. Please let's be assured that questions will be from this part of the chapter. So, this is the characteristics of TH1 on and off. So, outgoing thyristors was TH5, and then TH2, TH3 and so on. Accordingly, we will give the name. TH1 and TH6 will conduct. It is for the 120 degree mode of conduction. So, this is IA, this will be a square wave. This is IB, IC, that will be phase shifted by 30 degree, and I have drawn for current, you require to draw for the voltage RL load. Now, what are the difference of the current source inverter and the voltage source inverter? One is that you got a rectifier generally, or if you have a battery or the solar panel having a constant irradiation and temperature, then you can consider them as a current source, and then you have a huge inductor. This is the one of the detrimental part of the CSI, otherwise CSI has a huge advantage, but it is bulky as well as the costly. And then in case of the VSI, generally you have a rectifier. Rectifier will be followed by the inductance, that value is quite less, because you will have a 300 hertz ripple, 6 pulse ripple for this 6 pulse converter, and you have, if you have a multipulse converter which we have discussed, and this ripple will be considerably low, and here you require to feed it from the capacitor. Why? Because it is a two task. Please understand it that even if it is feeding a resistive load, so current and voltage, this is a voltage and this is a current. Here you, even though you have given a constant voltage and you are converting it into the AC, you are fetching maximum power that leads to discharge of this, somewhere this energy will come, and this will be feeding from this capacitor. Same way at the zero crossing, you do not have any power output, so capacitor voltage will little swell up, and it will be continue to be so. And for this reason, we require to provide a capacitor here. So, types of source, the current source Is is almost constant, voltage source is almost constant, we get a constant voltage source irrespective of the load, that is our assumption, and we manage it by the modulation. Output impedance is high. So, that is the one of the problematic entity here, the output impedance is generally high because of the high inductor, and here it is quite low. So, line voltage you essentially get a sinusoidal one, that is what I wanted you to draw that, and current with what you have drawn is a 120 degree mode of conduction, and you will get a this staircase waveform. And on the other hand, if you have a 180 degree mode of conduction, it will be same for the line voltage, but current will have a ripple and it will be close to sinusoidal because of the effect of the filter if you are feeding a RL kind of load, because most of the machines are essentially RL kind of load, thus you expect this kind of current waveform. And what else? The characteristics. So, this is the one of the major benefit of it. Easy to control the overcurrent condition with this design. So, there is no short circuit condition. Output voltage varies widely with change in load. So, this is one of the drawback also, because if you keep this constant, since current is constant, the voltage whatever will depend, it will depend on the load. Output voltage variation small because of the capacitor, capacitor will maintain the DC link voltage of this device. Now, we require to design the suitable control strategy for it, and we prefer we have a this much of the PWM technique, and also we have for the multi-level inverter that we will discuss later. Thereafter, we will discuss the PWM technique for the multi-level inverter also. So, we have a now let us concentrate on the basic PWM and its when it is operated, what is Fourier series analysis and how this will generate the harmonics. So, you have a single pulse modulation and you have multi-pulse modulation and the sinusoidal pulse modulation. We will be covering these two entities here, and others has been covered in the other lectures. So, let us talk about the single pulse modulation. So, there is only one pulse exists per cycle, and by this way you can eliminate one harmonic, like when you are playing guitars, you touch in a particular note and that it creates the it eliminates that particular note, particular harmonics from the system. Same way the width of the pulse varies to control the inverter output voltage. So, this is the case where you can have a triangle waveform and once you have switch it on, you get this kind of pulse, you have a phase shifted triangular wave. So, this and this and this. So, you get a waveform and you change the DC level. So, you get more the amplitude of the voltage. In that way you can control. Okay. So, frequency of the reference signal determines the frequency of the output voltage. So, this square pulses will have a frequency, and the ratio of AR to AC called the modulation index and controls the output voltage magnitude. And thus you can have, so this duration of 2D. So, ultimately this duration is like this, and in that way you can see the duration of this different part of this 2 pi modulation technique. So, ultimately you get 2 square wave. Now, if you generate this kind of waveform, that is what a square wave inverter is, and thus the power quality problem comes here. And for this reason we require to have a analysis of it. The output voltage inverter with a single phase modulation is given by V0, and since there is a odd symmetry n equal to 1, 3, 5 to infinity for Vs by n pi sin n pi by 2 sin n d sin n omega t. So, output voltage what essentially you will get is 4 Vs by pi sin d sin omega t minus, you will have a alternate plus minus, that will be 1/3 sin 3t sin 3 omega t plus 1 by 5 sin 5 d sin 5 omega t, thereafter minus 1 by 7, all those things will come, and the magnitude V01 will be 4 Vs by pi sin pi by 2 sin d sin omega t, and thus 4 Vs by pi sin d sin omega t, and essentially what you got is the magnitude of this fundamental, that is 4 Vs by pi. So, depending on the sin d, magnitude of the Vm is going to vary. So, if n d equal to pi and d equal to pi by n, then nth harmonic will be eliminated from the inverter. This is a simple logic. And for example, for eliminating the third harmonic, 3D equal to pi, that means pulse width will be 120 degree. So, you have to shift like this. So, this duration is 30, this duration is 30 and this is 30, 30, 60 and this weight 2D equal to 120 degree, and thus you can see that third harmonic will be eliminated. By this method you can only eliminate one harmonic from the system. So, this is the case. So, interface from single PWM, third, fifth, seventh harmonic dominates when voltage is reduced. So, once you voltage is reduced, so you are squeezing. So, large amount of harmonics is introduced for the lower amount of voltage range. You can see that this is a 180, this is a value of the 2D. If 2D goes to 180 degree, then there is a considerable less amount of the other harmonic. But if you come to this point 45 degree, then you can see that this one corresponds to third harmonic. Third harmonic is having a value of let us say 0.3 or 0.4, and this will have a value of 0.47. So, huge amount of third harmonic is present and THD is more, and the harmonic content can be reduced by having multiple pulses. For this reason, instead of the single pulse, we require to go for the multiple pulse to mitigate this power quality problem. Now, we have a multiple pulse. So, the multiple pulse modulation in this method, many pulses have the equal width are produced per half cycle. The getting signals are produced by comparing the referring signal with the carrier signals. So, this is a triangular wave, this is a square wave and there will be a comparator. So, comparator will give a trigger and you will on and off. So, you will have a 2D, D and D and D and so on. So, this one lambda is pi by 2D minus 3 plus D. So, this is the case. Now, we can do the Fourier analysis of these circuits and we can see that how it will give lower THD. So, this is the case. So, you will get a multiple pulses from there and the frequency of the reference signals determines the frequency of the output voltage. The ratio of AR and AC is called the modulation index and controls the output voltage. Now, let us do the Fourier series analysis of it. The output voltage waveform can be expressed in the Fourier series, where output voltage will be here. So, it will be n 135 to infinity 8 Vs by n pi sin n lambda sin n by 2 sin omega t, and thus you can have a extend it 8 Vs by pi sin lambda sin d by 2 sin omega t minus 1/3 sin lambda sin 3 by 2 omega t, fifth and so on. But here is a beauty, actually we can cancel few of the harmonics here and the fundamentals of this will be V0 1 and that will be Vs 8 Vs by pi sin lambda sin d by 2 sin omega t and Vom will be 8 Vs by sin pi sin lambda sin d by 2. So, this will be the magnitude or the amplitude of the fundamental voltage and thus you can control the magnitude of the fundamental voltage by D as well as by lambda. So, there is a both controlling unit. Now, for example, if you take 2D equal to 72 degree the single pulse modulation index peaks will be POM equal to Vs by sine, and that will be your 74%, so rather 75%, 0.784 Vs. And what essentially you get it here? It is little less. The 2 pulse modulation peak for the same value you will get is 8 Vs by pi sin lambda sin d by 2. So, lambda is 180 degree minus 72 by 3 plus 36 by 2, it is 54. So, if you put this value you will get 63 degree, around 15% less you will get. Are you happy with that? That is different question. So, what we can conclude, but there is a way to eliminate the multiple harmonic here. So, you can choose in such a way that the third harmonic will be eliminated. So, 3 lambda can be 180 degree, and also you can choose 5 d by 2 is 180 degree. So, in that way, or 7 d by 2, any of the 2 frequencies you can eliminate by it. So, that is called selective harmonic elimination, that has been discussed in our class in detail. So, what we can conclude now? It is seen that from the above fundamental component, the output voltage is lower for the 2 pulse modulation than it is for the single pulse modulation. Single pulse modulation you get around 75% with the same duration, but that is a catch here. The lower order harmonics are eliminated and higher order harmonics are increased, but that is not a big deal. Eliminating higher order harmonics are easy, because designing a low pass filter, essentially motor, power system, all are low pass filter, and thus you get rid of those waves, but higher order harmonics can be filtered easily. So, for this reason, for the sake of compactness, the size of the filter will be bulky if you use a single pulse, but if you use a multi pulse you get a little less voltage, but your size of the filter will be less. This scheme is advantageous for this reason than the single pulse modulation, and ultimately you cannot fit in motor, you require to fit it to the filter. Designing a filter is a challenging job, but large number of pulse per cycles require frequent turn on and the turn off of a thyristors. If you are using thyristors, then you require to have a commutation circuit, then again it makes the system bulky, and thus and also it will increase the device. It is also you require to maybe switch over to the, instead of the thyristor, to GTO or any turn on and turn off devices, and thus what will happen then, we have to reduce the lower rating devices for that reason, and moreover you will have more switching losses. So, this is some way we require to do some kind of compactness studies for it, so that which one we will go for it, and thus what it is, this will increase the switching loss. This is the major disadvantage of it. Thank you for your attention. We shall continue to our discussions on the on this power quality issues. Today I try to cover the CSI and the VSI. and the elementary PWM and its effects to the power quality. Thanks.